I would say 4.
Okay, so you put a 4 in front, and?
And came up to 4 carbons on the reaction side.
Okay.
8 oxygens on the reaction.
Well, so far, that's not including hydrogen.
Yeah.
So we did carbon first, and then what?
Then I multiplied 5
To the hydrogen to make it 10, right, with our hydrogens on that side. So then total oxygens on this side is what?
13.
So 8, and then 5 is 13 oxygens. And so you would want to put what here?
6.
We would put 6.5, but we can't put halvesies. So then to make it fully balanced, you have to go through and do what to it? Double it all. So 2, that's 13, that's 8, and that's 10. So 13 should be our final answer there. D. All right, give me a thumbs up if you got that. Okay, okay. So let's keep going. If 10.3 grams of sodium hydrogen carbonate reacts with excess hydrochloric acid, a white crystalline substance is produced and the mass of the product is 7.59. First off, what kind of reaction is it? So I'll let you guys work through that for a second. You might want to write down the reactants and products. Hydrogen carbonate is the same as bicarbonate. It's just like actually easier way to say it. It says the hydrogen in there versus the bi. Talk to your groups if you need to. Because this right here is the anion. What is the formula for hydrogen carbonate, like together as bicarbonate? HCO3 charge 1 minus, which is the charge of sodium, or what's the ion of sodium? Na1 plus. Okay, so put that together. That's your sodium hydrogen carbonate, which is sodium bicarbonate, and add an HCl and do the reaction that you think applies based on your 5-type reaction genome. That's just the reaction. No, I mean like how is it? All one yes. I just wanted to give you the ion. That's why it's 2 times. No, it's not one thing.
A white crystalline substance it's just saying
Go ahead and proceed for the rest of the problem if you're able to.
then you have to start I think it would be
All right, who can tell me the 2 reactants? I got one of them kind of for you. Go for it, Jillian. HCl, beautiful, hydrochloric acid. What kind of reaction is this, Chloe? Based on the way it looks right here, what type of reaction is it? So you saw that because you see that there's a ion and then another ion, and then acids act ionically. You know that's how you get your crisscross of the subscripts. They act like ions. So there's our ion, 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 ion. This is a cation, anion, cation, anion. So who must recombine, Margaret?
Sodium.
So sodium and chlorine, and that's a 1 plus and 1 minus, so we immediately say it's 1 and 1. Easy. What else?
And then hydrogen carbonate.
So hydrogen carbonate and hydrogen. Now this is the positive one, right? This is the negative one. Which one goes first? So you would probably initially write HCO3. But a lot of times we don't duplicate our letters, we just put a 2 with it, right? So what would that be? H2CO3. What is the name of that? It's an acid, remember? It's got an H in the front. It's an acid. So that was hydrochloric acid. Hydro means binary acid. You have to say hydro to indicate there's 2 elements. Is this binary? So do you say hydro? You shall not. Carbonic acid, right? So carbonic acid is what you find in your soda. It's what makes it bubbly. But those bubbles are made of what? Yes, but what's the gas? It is a gas. It does make a gas. What's in the bubbles? It's a carbonated beverage, right? It's carbon dioxide. So this actually is so unstable. It doesn't exist in nature as carbonic acid. It actually further breaks down to make a gas. Thanks for the spoiler there, Jacob. So carbon dioxide is the gas, and then what else is in this that could be a separate product? So you see the hydrogens and one oxygen. What is it? Water, H2O. So this is actually a double replacement reaction, which we made the 2 products, and then we're like, oh, well, this carbonic acid, which I wouldn't expect you to know right now, but we're going to kind of see this in the lab later. The carbonic acid doesn't exist for very long. It immediately produces bubbles and water as a product. So that really solidifies the white crystalline solid that you know is there, because it's definitely not the carbon dioxide, because what is that at room temperature? What state of matter? That's a gas. What's water at room temperature? Liquid. And so this is likely the solid white crystalline solid product. Yes.
So instead of writing carbonic acid, you write water and carbon dioxide?
Yep. And that would just really help with understanding what's actually happening in that reaction. Okay, so we have our
3 products.
There are 3 products. It was at first a double replacement where we made 2 products, but then I helped you guys understand there was a little bit more to it. Yes.
I'm looking at the solubility rules. NaCl is.
So this is what I'm going to tell you about, okay? So the solubility rules do say all chlorides are soluble except for the heavy metals. And sodium metal is definitely not one of the heavy metals. It's an alkali metal. It is aqueous at room temperature. But this, okay, so this doesn't tell you everything that's happening in the lab. A lot of times reactions like this is actually a lab we'll do hopefully later this week. We'll actually heat it up so much we drive off the carbon dioxide because it's going to bubble up anyway, and then we'll drive off the water, meaning it gets evaporated. So if salt water, think of like going to the ocean and coming out of the ocean, the water evaporates, what's left behind? The salt, right? The sodium chloride in this with respect to this salt. So it does form a solid white crystalline product because you had to identify which one of them it would be. Definitely not these 2, so by default it has to be that one. So good point, Nick. I didn't tell you the whole story. There's some dehydration going on here. All right, so what's the identity of that? Sodium chloride. Give you a little nomenclature review, and then based on the data, determine the molar ratio between the product, the given reactant, and the product. So how would you figure that out based on numbers? Tell me the process here. So Tim, tell me where you think you would start with that. Well, it says between the given reactant, which was sodium hydrogen carbonate, and the product being asked of, which was sodium chloride. So from our balanced chemical equation, we can see it's 1-to-1. But how would you show that from data, the data given? Because this is a data-driven question. So 10.3 grams of sodium bicarbonate, and do what with it? So find the molar mass and convert to what? Moles. Okay, so 1 mole of that. $36 plus 48. 72. 82. I think it's 82. So let me double check that math real fast. Okay, so you convert that to moles, and then separately, so that's our reactant, and then what else would you do, Kim? So take the 7.59 grams of what? And convert it to moles. 1 mole of sodium chloride is 58.55. Yeah. Something like that.
What
Yes.
does that say on the bottom?
82. I think it's
Oh.
82. Did anybody verify that? Molar mass? Yeah.
74.01.
What's 23 plus? I mean, what did I say? 36 plus 48. Is that what that is?
Yeah.
You got 83. I thought it was in the 80s. Okay, guys. You know, mental math. I'm just close. Okay. So 84 grams apparently. That helps me out there. All right. So then after that, Kim, you're right. You take it both of them to moles, and then you'll compare your moles to get the smallest ratio between them by dividing by our smallest number of moles. Where have you heard that before? Divide by the smallest number of moles. Singing? You know this. You kind of said it. Empirical formula, and that's kind of understanding empirical formula is the simplest ratio within a compound, whereas a balanced chemical equation is just the simplest ratio within a reaction where your coefficients are simplified to, I'm not doing 10, 5, 10, 5. I'm going to reduce those down to 2, 1, 2, 1. So that's what we do there. Okay, let me get one more question out of you in terms of review of old stuff, bringing into new. I'm just going to go forward. I'm not going to finish calculating there. I think we know our process there. Oops. So this one's pretty easy. Chemical changes. Okay, so go ahead and read number. I'll read it to you guys, but you guys look at the answers. A student mixes, this could be you. A student mixes 2 chemicals in a test tube. The test tube turns hot and bubbles appear. What indicators of chemical reaction is the student observing? Don't say that loud yet. Just give it a second. Robbie, what'd you say? A, B, C, D. D. Okay, so what's the term that would be used for a change in temperature based on the test tube turning hot? What kind of reaction is this? Ooh, it's actually, so it doesn't say it's not combustion, but it says it mixes 2 chemicals in a test tube. Oxygen is really hard to contain, right? The gas can be floating everywhere, so that would be hard to add to a test tube. So I'm looking for, is it endothermic or exothermic? Because the heat's going out, right? It's exiting. This was based on your review of your notes you guys took by yourself. This exothermic has a delta H, enthalpy, delta H, of a sign of positive or negative. If heat's exiting, do you think delta H should be labeled a negative or positive? A negative, and you can look back at your notes for that. That is a negative exothermic reaction. Energy is being released to the surroundings, which are the test tube and everything else. What indicators of chemical reaction system observing as well? It says bubbles appeared. Bubbles is a not fancy word. Formation of gas is a little fancier. What's even better than that? Gas evolution. I was waiting for you. Okay, thanks. Okay, so gas evolution. So in this case, they're seeing the bubbles form. So assuming that these two are a liquid plus a liquid yields a gas, and I don't know, I'll say an aqueous solution. Thinking about your entropy, which was delta what in your notes that you guys took by yourself? Delta, we did delta H, which was enthalpy or enthalpy. Delta, can you look back at your notes? I'll wait on you. Trying to hit the highlights here. Come on, Chloe. S, thank you. Okay, delta S, that is a measure of what? Entropy is a measure of, so we're talking about enthalpy versus entropy. Disorder, right? So usually by the end of the day, my room has satisfied the universe, which is the universe always wants energy to be released to itself, to the universe. But with that, it also wants a lot of disorder. So usually by the end of the day, my room has satisfied the universe because it is a mess in here. But just like your room at home, it naturally goes to disorder. It doesn't clean itself up. That would be amazing, but it's never going to happen. So in this reaction, we're going from liquid to gas and aqueous. What happened to our disorder based on the arrangement of those chemicals with each other? How did it increase?
Well, there's more like in terms of phase, we're going from solid to liquid to aqueous to gas.
Mm-hmm.
Is an increase in the phase.
So it's an increase in their arrangement with each other, right? So an increase in the disorganized pattern that they're arranged with each other. So liquids are kind of organized, solids are like super organized. Gases are crazy people, they're everywhere. And aqueous is just as crazy. Basically, it's got ions mixed with water, it's pretty disordered in relationship to the other one. So yes, the entropy increased, meaning the disorder increased. That's actually something that satisfied the universe. So in your notes, do you guys remember putting smiley faces? Yeah, okay, the universe is like, yeah, increase in disorder. What about this one? Is this good or bad for the universe? Say again? Good, yeah, the universe wants the energy to be released from the reaction. That poor reaction, it can't have too much energy within it, it's just not stable that way. So this is a good thing. So would this reaction be spontaneous? Would it be favorable to the universe? Double whammy, happy face? Yes. Okay, so it'd be yes, spontaneous. And that's what thermodynamics is a comparison between the enthalpy and the entropy to see if the reaction would occur. And obviously it did. It happened without any intervention, because that reaction immediately, when you put test tube 1, test tube 2 together, it wasn't like, hold up, let me wait and think about, am I going to react? And I just reacted. It created heat and formed bubbles, which was an observation we made for chemical changes. Yes. Yeah, I'm going to keep embedding it throughout, though, because it's relevant to about 3 or 4 units that we work through. I just want to give you the vocabulary so we can actually speak the same language at this point. Okay? All right, so let's wait on that one. We'll wait on these. All right, so here's what I'd like to do. Give me a hand, or raise a hand. You need my assistance with your problem. A couple groups. Okay, raise your hand if you just need to get that thing on paper. Raise your hand if you don't have any idea what I'm talking about. Thank you. Okay, so everyone knows what they need to do. I've spread out some things. I'm going to put a timer on for about 20 minutes first to kind of see where we are, to get a temperature of where we are. I do think if you collaborate, if you want to work on different pieces of paper and then tape them all on your library paper, that might be more effective than one person being a sole writer. So kind of make sure you collaborate, but like Kyle do all the work if he really wants to. So just make sure you're doing that with each other. You have your rubric, you know what I'm looking for, okay? I'm going to be around to different groups, so please go ahead and start with that. I've spread everything out for you. You need to find your poster. Leave your homework on your desk for me. Leave your homework on your desk. Keep it on your desk right now. Keep your PS12 and your video notes on your desk so I can see them. Oh, let me take a 10 minutes. Is Caleb? Pretty. Caleb's not here. All right, so hopefully you've had a minute kind of change your brain back from stoichiometry to states of matter that you kind of have a baby bit of background information on. So if we're comparing states of matter, not only are we comparing their different characteristics that they have individually, but also how do we get from one state of matter to the other state of matter. And so a lot of this is background. If I want to get from solid to liquid, what would I call that? Melting. That's the phase change called melting. If I want to get from liquid to gas, what's the term that talks about going from liquid to gas? Vaporization or evaporation, kind of being the same thing. So not only are we talking about the individual states, but how do we get from one state to another? So pretty easy background, but we have diagrams that help us represent this appropriately. So one of the diagrams, this is not a true diagram, this is one I just want to show you. Now you should know all of these state changes, and if you'd like to write on the back of that sheet, that's up to you. I'm going to give you some of the brief notes today. We'll pick up the rest of them tomorrow as I kind of come up with plan B for tomorrow in terms of finishing our posters too. So if we're going from solid to liquid, we call that melting. But inverse that, from liquid to solid, we call that freezing, right? Common knowledge, you know that? That's easy. If we're going from liquid to gas, we call that vaporization or evaporation. If we're going from gas to liquid, you call that condensation. And those are terms I think you're familiar with. Tell me if I'm wrong. Give me a head shake. Okay, cool. And the last one, plasma, I'll get you in a second. So the process that could occur, we don't see too often, and I didn't get a chance to go to Harris Teeter this morning to bring in some dry ice, but dry ice is a solid block of carbon dioxide. And that's the foggy smoke stuff you see like out at Halloween, at who's ever in the Rainforest Cafe? Rainforest Cafe? Oh, if you guys have never been to Rainforest Cafe, you're missing out. You gotta go sometime. They have like this like smoky kind of fog coming out of there. They have like animal displays everywhere. It's dry ice. So basically it goes straight from solid all the way, skips through liquid phase, straight to gaseous. And that's called sublimation. And an example of that would be dry ice. If you're wondering, it's carbon dioxide solid to gas. And the opposite of that, going from gas to solid, is called deposition. And so deposition is something you don't see a lot of, but you can think about like frost forming on flowers and plants and stuff outside. It's coming from gaseous water particles in the air, and that's that foggy kind of haze, and it immediately precipitates to the grass or to the plants or the vegetables like in the garden. Outside, that's frost. So it goes straight from gaseous water to solid water. It doesn't really freeze, it deposits. Another example of sublimation is, who's ever used an air freshener, those like solid air fresheners in your car? Okay, do you see it turn liquid, or do you just smell it automatically? You just smell it. So it's going straight from a solid phase on the air freshener like that. Those, I think it's called resonance. Those are like little triangle ones with the caps on them and pull off. You guys know what I'm talking about, those air fresheners? Okay, any air freshener will do. But it goes straight from solid phase to gaseous phase. No liquid phase in the middle. So that might be a good example. Okay, so relatively, yeah. That's basically how deodorant works as well. Anything that's, so the deodorant has different components within it. It's got like lipids that are like kind of oily and stay solid, and then fragrance particles, which are, sometimes they're kind of liquidy, but they also can be solidy, and then they turn right to vapor from your heat of your body. So thank you, chemistry, for making me smell good. Okay, so if I'm going to talk about the relative energies of solids, liquids, and gases, who's the most energetic state of matter? Gas, right? So these are high energy. Okay, who's the least energetic state of matter? Solid. And I do think that you should write down some of these diagrams or the processes, because this really pulls together the big picture. And big picture is way more important than small picture. You know, you'll remember the big picture for the rest of your life. The small pictures you might forget. So if I have to get from, I don't know, I put solid, I meant low energy. Sorry, low energy is the solid state, high energy is the gaseous state. How do I get something to go from the low energy state to the high energy state? What do I have to do to it? Say it again. How do I excite the particles? Heating them up, right? Giving them energy. So heat energy is sometimes correlated with increasing temperature. Sometimes it's just an inherent amount of energy that they can kind of attain from other ways. But if I want to go from a low energy state to a high energy state, I have to add energy. And I'm going to say add heat, since that's the term energy that you guys are using right now. Is that an endothermic process or an exothermic process? Endothermic process. This is probably the part where you're like, okay, now we're really hitting that review that she was talking about delta H and delta S again. So if we're going from a low energy state like a solid to liquid to gas, we have to add energy. Adding positive energy is a delta H process that has a positive value associated with it. So the enthalpy is positive. That's called an endothermic process. And I'm going to put process here on purpose, because what you'll notice is that we are not talking about a reaction here, right? It's just melting, and then it's just turning to gas. It's not a reaction. Reactions are synthesis, decomp, combustion, double, single replacement. This is just a process. All right, so opposite, you guys can help me out there. Going from a high energy state to a low energy state, what kind of terminology can I add here? It's an exothermic what? Process. Okay, so it's an exothermic process. Okay, what else? Since they're saying adding heat, you're going to be, okay, so I'm going to say releasing energy, and you can put energy as heat or just energy in general. It's going to be releasing energy. And that's that release, that exit refers back to the exothermic process. And what would the delta H sign be? Negative, because it's releasing, it's exiting. So you should be able to associate these terms and these signs to each other, and then these terms and signs of the delta H value to each other. So that's not too bad, right? Kind of commonsensical. Now, if I wanted to assign a number to this, I can call them different things, but they're really the same thing, but in reverse. So these delta H values, delta is a triangle. It's delta H, which is change in enthalpy. So there's a couple of terms you'll hear me say, but they all are referring to this delta H. So change in enthalpy is what delta H stands for. So if you told me that there's a delta H of vaporization and there's a delta H of condensation, that's just labeling the process that it's referring to, right? This one's going to be positive or negative if I'm vaporizing something. Why positive? It's adding energy to a liquid to make it turn to gas, right? So this is a positive value. And if I'm condensing something from what to what? Gas to liquid, what's going to happen? It's releasing energy, right? So this is going from gas to liquid. This is going from liquid to gas. This is going to be releasing energy. But aren't they exactly the same process, just reversed? Right? They're exactly the same. Now, I would have to be talking about one particular compound. Like, let's just say water. I'm just talking about water. If I'm vaporizing water, it takes, this is from memory, so forgive me, 40.7 kilojoules kJ, per 1 mole of water. Okay, 40.7 kilojoules per water. Write that down. And that's a positive value. 40.7 kilojoules per 1 mole of water. 40.7 kilojoules. Okay, so that's a positive value. So can you think about what would happen, what amount of energy would be released in the condensation of water? Same process, different. Don't inverse it, just inverse the sign, which we've already done, right? Same amount of energy, exact same amount of energy. So 40.7 kilojoules kJ per 1 mole of water. Except this one's negative, whereas this one's positive. So we're learning about how do we relate phases of matter to other phases of matter, and also the energy changes that are associated with those phase changes. So all of this is just numbers and words, and there's got to be a better way to organize our thoughts here. So with this, there's something called a phase diagram. So let's talk about the phase diagram first, and I'll show you the heat graph. There's a lot of diagrams in this, and I'm going to do a lot more of the information for you, but I'm just not ready to do that with you yet, because in terms of starting gases and states of matter was not on my to-do list today. I was going to finish stoichiometry with you, but we're going to kind of do both because I don't think we're ready to finish up stoichiometry all the way yet. So this is your chart, right? This is what you're just filling in some pieces of. I would say there's only a couple pieces that you maybe didn't think about, and it's about the motion of particles being absolutely, supposedly, very little motion in solids, but we could talk about the vibrations that exist. So the vibrations in a solid are what make it inherently have a little bit of energy. So all solids have a little bit of energy. But this tape dispenser, which is just solid in general, its particles, they're moving. Just little teeny bits are vibrating, but they are moving. And my hand particles, they're moving. If these particles didn't like each other just as much as they did, my hand didn't like itself, I could go right straight through the stapler. Through the tape dispenser. I could walk straight through Jillian's body, but her particles like each other more, and my particles like each other more. So once we come in contact with each other, it's like, oh no, I'm not going to separate and go through her body. But I could if my particles were just like, yeah, I'm good to separate. If you're good to separate, we'll just kind of walk through each other. But our particles they can move, they can separate apart and move through things. Dun, 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 you're a ghost. No, okay, you're not a ghost. You're not in a dream. Okay. Second, you can talk about how the liquid particles, of course, as they start to attain more energy means they're able to move more. And as they move more, they take on a fluid appearance. And fluid is a term that actually describes both liquids and gases. The word fluid describes both because it's talking about the motion of the particles, not the thing. It's not the matter. And so both liquids and gases can take the shape of their container. So like this coffee cup, a gas can take the shape of its container. The liquid, if it's full, can take the shape of the container. And solids don't necessarily take the shape of their container. If I put ice cubes in here, they're not going to morph into a cylinder. That would be really cool, but they're going to look like an ice cube like it looked like to begin with. So solids don't necessarily take the shape of their container. Gases are in constant random motion, meaning they're bouncing off the container walls at all times. That's how balloons stay inflated, right? They bounce off the container walls and they keep that balloon the shape that it takes. So tell me about a solid. If I have a solid in my hand, so you have your pencil in your hand, squeeze it, okay, you're increasing the pressure on it, what happens to it? Say again? I heard nothing. Does anybody else concur? Nothing. Most of the time, high pressure does nothing to our solid because this is, I'm just going to put an arrow, increasing pressure does not change shape. Delta means change as well, okay? So change, if you increase the pressure on a solid, it's really, unless it's Play-Doh, okay, it's not going to really change its shape or its volume because those particles are already so darn close, they can't get any closer, guys. We're not going to start to fuse nuclei and do nuclear fusion in here. They are so close, they're not going to change their shape. But what about a liquid? If I put some pressure on a liquid, is it going to change, yay or nay? Can the particles get any closer together? Just a teeny bit, right? But you also can change the shape of the container, that's about it. Okay, so if I take a can and I squish the can, the liquid's going to squish a little bit with it, but then it's going to start to spill out, right? So you're not going to just totally change the shape of a liquid. So increasing the pressure changes volume very little because you're not going to squish the volume down. It's going to start to spill out of the soda can. There's no way you're going to make the volume decrease severely. However, if you have a gas, you guys, I didn't tell you this today. Can you guys bring your box of gas? You got your box of gas? You all have it today. Whip it out. You got your box of gas. Okay, you got it. I didn't have to tell you to bring it. You always have your box of gas with you. Okay, these gas particles are all surrounding each other. They're, one's here, one's here, one's here, one's here. They're everywhere. Can you increase the pressure on your box of gas? Do it. Okay, what did you do to your gas particles? You what? You moved them together in this little box. Okay, now they're condensed in this little box. Now they're closer together. Did you change the volume of your box? Yes, you are like, squish together. Okay, now release that pressure. Oh, what happened to the volume? It increased, and the gas particles can kind of bounce everywhere. They're not condensed together. Okay, so if you increase the pressure on your gas, what happened to the volume? It got smaller. What's a term that describes when two variables are oppositely related? Inversely, there's another term too. It's basically the same term. Inverse or indirect, right? Not direct, indirectly related. So these variables of pressure and volume, which you saw on the fish's eyes popping out of its head and then being put back in its head, through the pressure changes, the volume of a part of gases can change based on pressure a lot. It's a lot more noticeable than pressure changes on solids and liquids. That's simply because they are loosely held together, whereas solids and liquids are a little bit more tightly packed together. They just don't have place to go whenever you squeeze their pressure together. And so what you also might notice is that kinetic energy, which is energy of motion, which you'll see on your reading guide when you do it, the energy of motion is more related to the particles being spread way apart, and as the particles are spread way apart, their attractive forces weaken. So who has the strongest attractive forces? Solids. Who's the weakest attractive forces? Gases. So if you didn't add this little part to your chart, you might want to do that. It is common sense, I think, as well, but sometimes writing down common sense means that you've agreed with it. You've decided that's a true statement. I'll talk about the bottom pieces in a second. So let's talk about the last thing I'll do right now, because I have 5 minutes left, is show you this. Now your diagram on your paper is a little bit dark. It's hard to see the differences. So if you want to re-sketch this in the back of your paper, that might be helpful. And so this is something called a phase diagram. You saw a phase diagram in your video notes, yes? It will always be set up the exact same way, but you should notice those standard sets of how you set it up. You have your pressure. In this case, it's in atmospheres. ATM is atmospheres. Like we live at sea level, which is approximately sea level. We live at about 1 atmosphere of pressure. But under the ocean, what happens to pressure? it goes way up. So if you ever dive, like scuba diving, your ears are like popping because it's like you gas inside your head, gas pressure on the outside. There's a pressure difference, so you have to pop your ears to make it like equilibrate the pressure. If not, your head will implode, your head will explode. So your ears are like, open your ear canal so the pressure equilibrates. And then on the bottom axis, you have temperature. And in this case, we're not talking about pressure and volume. We're talking about pressure and temperature and how do they play a role with each other. They do relate to each other. So if I have some gas particles and they're in my box and they're chilling, what happens to them if I heat them up? What do you think's going to happen to those gas particles? Okay, so did anybody else want to answer that? I got one person. If I take my gas particles, they're in this box, and I put some fire underneath them, what's going to happen to those gas particles? They can't really change phase, right? So what are they going to have to do? Speak your mind. Let's go. They're going to move faster. Thank you. It's okay if you're wrong. Just say it out loud so the rest of us can learn from you. So that is right. They move faster. Well, if I move faster, what's going to happen with my container walls? What are they going to do to my container walls? Well, before they add to pressure, what are they going to do with the walls? So they're just bouncing around like crazy, right? So if you speed up your particles, you increase your temperature, increase your speed of your gas particles. And as they increase their speed, they hit the container wall a lot more frequently. If you increase your frequency of collision with the container wall, that actually increases your pressure. And that's what you see as a positive relationship here, a direct relationship. And that's actually, as you increase temperature, most of the time our pressure will be increasing. That's why our gas pressure is increasing. That's not the point of today, though. I want to make sure you understand how to read this phase diagram, and then I'll leave you alone. So if you've got a chance to sketch it out for yourself, you have solid, liquid, gas. These solid liquid gases have lines between them, and those lines between them are the phase changes. What is the phase change between solid and liquid? What's that term? Melting. So if we are melting something at 1 atmosphere, it's not going to occur at every temperature. It's going to occur at one specific temperature, and that's where the axis crosses. So at 1 atmosphere, where does the solid to liquid phase interface? Where does it occur? It's at this point. Well, then all you got to do is go all the way down. I might need to expand my graph here. So here, that temperature, as you drop down, is at 0 degrees Celsius. What thing melts at 0 degrees Celsius? Water. This phase diagram is very specific. This one's only for water. There's different phase diagrams for every element, for every compound in the world, because at everybody's melting point or other points, freezing point, vaporization point, they're all different. Okay? So let me tell you what I want from you, because I got to push about 3 minutes. So I want you to think about your videos. Keep your video notes for now, because I think this is useful for this. What I want you to attempt for me tonight is the questions that are right underneath it related to the phase diagram and then to the heat curve. Try those. We're going to go pretty in-depth tomorrow about reviewing this, and I have another practice sheet with diagrams with it. I want you to at least get exposure to the 3 other sheets these are referring to. And if you don't, it's okay. We're going to kind of recap those all tomorrow, but I want you to attempt them. Problem set 12, I will take tomorrow from you. So if you have some questions on problem set 12, stop back in during your lunch, because of course I don't have teal. After school I have a staff meeting, so it's one because I have no control over. If you want to pop in for 5 or 10 minutes during your lunch to get some questions answered, I have to go through your planning, so I'll just work with your schedule. And I will take problem set 12 tomorrow from you. Wait. And then reading guide 13. If you did not do that, if you're watching videos, you have to finish a couple other things. Reading guide 13 is due tomorrow. That is our new unit called states of matter and then eventually gases. But that's kind of what we used to do. So I think reading guide 13 would be quite easy. So if you want to put your laptops up, make it happen.
So, what are we doing on here? All right.
That's what's being on the sketch. And I'm videoing right now too, I can always put it up. It's A is right here. I'm sorry, this is the different one. Let me pull it up, that one. There it is. A is right here. B is right here. C is right here. Nope. Yes. D is over here. I think that's everything, right? Okay, so that's A to B. If you want to take a picture of this, I'm not sure if it'll be really clear, but you can try. A little bit better for you. And if you started your gas well potable, you are ahead. You're awesome. We will pick that up probably on Thursday or Wednesday. Take a chance to breathe. And think to yourself on how you're going to handle this no chill week. And convince the freshmen that it's not cool.
Why would they call it next week?
They don't care.
Huh?
Would you like right in the middle of the week?
Because it's not immediate. It's not immediate punishment. Have a good day, guys. Chloe.
We're so cool, we're gonna throw this trash everywhere.
Possibly lunch. Possibly lunch.
Yeah, maybe.
Or talk to a peer. But it got